Welcome back to the Deep End. Today, we are doing something a little bit different and honestly something a little bit wild. Usually when we meet here, we are combing through established research, the big academic journals, peer-reviewed studies, the drill. We like solid ground.
Right, the stamp of approval from nature or science.
Exactly, we like that. But
Yeah,
today, we are stepping right off the edge of the map.
we really are.
We're looking at a set of 3 draft papers that are attempting to do nothing less than rebuild the laws of the universe from scratch.
And when we say from scratch, we aren't exaggerating. I mean, this isn't just tweaking a variable in a known equation to make the data fit a little better.
No, not at all.
This isn't someone saying, oh, maybe the electron is slightly heavier than we thought. This is a complete reimagining of the mathematical structure of space-time itself.
It's like looking at the foundation of a house and saying,
what if we didn't use concrete?
what if we use something else entirely? It's absolutely fascinating.
It is.
I spent the weekend reading these, and I felt like I was watching someone try to build a skyscraper using only, a screwdriver and a dream.
Yeah, that's a great way to put it.
The papers are titled Split Quaternion-like Extension of the Complex Plane, Lorentzian Cosmological Model, and Cosmological Evolution of Lorentzian Spacetime.
A mouthful, I know.
And the goal here, the mission, if you will,
Yeah.
it seems to be unifying the Big Bang, special relativity, and even hints of quantum mechanics into one single 5-dimensional geometric structure.
Exactly. The author, who we only know as anonymous author, essentially attempts to embed our familiar 4-dimensional reality, length, width, height, and time, into a larger 5-dimensional framework.
A framework they call Space-Time Ultra.
Space-time ultra. And the claim is massive. The claim is that by doing this, you solve some of the biggest headaches in cosmology like dark energy without actually needing dark energy. It all just, it falls out of the geometry.
Okay, let's unpack this right away, because the backstory here is almost as interesting as the math itself. You pointed out the special thanks section in these drafts to me, and I literally laughed out loud.
Good.
Not in a mean way, but just out of pure delight.
It's so different.
It was so refreshing compared to the stuffy academic papers we usually read.
It is quite something. In the world of academia, you usually see acknowledgments to grants, universities, famous professors, funded by the National Science Foundation.
Right, the usual suspects.
Here, the author explicitly apologizes for not having a bibliography or citing other modern researchers because, and this is a quote, they do not exercise a research position and simply cannot afford the journal subscriptions.
I love that. It is this total outsider science vibe.
Totally.
They mentioned they learned everything from textbook mathematics and YouTube content creators.
Yeah.
It's pure curiosity driving complex math.
It reminds me of those stories from the early 20th century, like Ramanujan, just, deriving theorems in complete isolation.
It feels very punk rock.
It is a romantic image, isn't it? But I think that context is so important to keep in mind as we go through this. This is a first principles approach.
Yeah.
Because they aren't part of the academic machine, they aren't burdened by the standard ways of doing things, they are looking at the math of general relativity and asking, what if we built the foundation differently?
They aren't worrying about getting tenure.
No, they're worrying about whether the equations balance.
And the promises made in these abstracts are huge. We're not just talking about some neat math trick.
No, not at all.
We're talking about a model that predicts the expansion of the universe, the stuff we usually attribute to dark energy, just by tweaking the speed of the universe itself.
That's right. They claim to derive a scaling factor curve that matches the standard lambda CDM model. That's our current best model of the Big Bang, the one NASA uses.
A gold standard.
It is. They also derive a universe with well-defined density and pressure, and in the second draft, they even managed to make the universe Ricci flat, which is a holy grail condition in gravity theories, by curling up an extra dimension.
So, to sum it up, we have a self-taught, independent researcher, a 5-dimensional universe, and a math trick that supposedly explains everything from the Big Bang to quantum mechanics.
That's the pitch.
I'm ready to dive in. But we have to start at the bottom. Where? Where does this even start?
It starts with a math problem, or rather, a reimagining of a very, very basic mathematical tool, the complex plane.
Okay, complex numbers. Flashback to high school algebra. Normally, when we think of complex numbers, we think of the imaginary unit I, right?
Right.
Where I squared equals -1.
Correct. That's the standard foundation of complex analysis. You have real numbers like 1, 2, 3, and you have imaginary numbers based on I. When you combine them, you get the complex plane.
And geometrically, this is perfect for describing rotations.
Perfect. If you multiply a number by I, you rotate it 90 degrees on a circle on the graph.
Right, because if I rotate 90 degrees twice, I've turned 180 degrees, which is like pointing in the opposite direction, which is like multiplying by -1. That logic always made sense to me. Times I is -1.
Precisely. Standard complex numbers are circular. Everything revolves around that circle logic. But our author starts by saying, let's look at the equation ZZ equals -1.
Okay.
They introduce a new unit, which they call L1, but here's the twist. L1 squared doesn't equal -1.
Oh.
It equals +1.
Wait, so it looks like a complex number, it acts like a complex number in the equation, but when you square the unit, you get a positive.
Yeah.
That feels illegal.
It feels illegal if you're used to the standard complex plane, but mathematically it's a totally valid structure. And this one small change is massive. It moves us from the realm of standard complex numbers into something called split quaternions.
I've heard of quaternions. That's what they use to program video game graphics, right? For rotations in 3D space.
Exactly. Standard quaternions are just an extension of those circular complex numbers. They handle rotations beautifully.
But split quaternions.
They aren't circular, they are hyperbolic.
Okay, you're going to have to break down hyperbolic for us. I know a hyperbole is a shape, those two curves facing away from each other. But why should we care if our numbers are hyperbolic instead of circular?
Because space-time is hyperbolic. That is the fundamental insight of Einstein's special relativity.
Ah.
Time behaves differently than space.
Give me an example. How does this math map onto reality?
Okay, think about Pythagoras. If you want to measure the distance between 2 points on a flat piece of paper, that's Euclidean space, what do?
You measure the change in x, square it. Measure the change in y, square it. Add them together, take the square root. A squared plus b squared equals c squared.
Right, standard geometry, the hypotenuse. But in special relativity, when you measure the distance between two events in space-time, say a light turning on here and a light turning on over there, you don't add the squares.
You subtract the time component.
You subtract it. The formula looks like x squared plus y squared plus z squared minus t squared. Ah, right. The space-time interval. That minus sign is the difference between space and time. It's the reason we can't travel faster than light, basically.
Exactly. That minus sign is the signature of Lorentzian geometry. It's everything.
Yeah.
And the author points out that if you use standard complex numbers with I squared equals -1, you have to artificially insert that minus sign to make the physics work.
You have to force it.
You have to force the math to fit the universe. You have to cheat a little bit.
Okay.
But if you use this specific math, this split quaternion setup where L1 squared equals +1, you naturally derive that subtraction.
So you don't have to force it. It just happens.
No forcing required.
Yeah.
They show that if you take a number in this system, say a plus b times L1, and multiply it by itself using their rules, specifically the conjugate rules, you naturally get a squared minus b squared.
Wow.
That minus sign appears organically from the algebra.
That is a pretty cool aha moment. So the math itself already knows the difference between space and time before you even start doing physics with it? It does. The draft emphasizes this over and over. This math naturally separates invertible vectors from light-like vectors. In this system, light-like vectors are what mathematicians call divisors of zero.
Divisors of zero. That sounds ominous, like a villain in a fantasy novel. I am the divisor of zero.
It just means that two non-zero numbers can multiply together to get zero.
Which shouldn't happen.
In normal arithmetic, that's impossible. If a times b equals 0, then either a or b must be 0. But in split quaternions, you can have non-zero numbers that multiply to 0. And in physics terms, this represents the speed of light.
How so?
It creates a rigid structure where the speed of light isn't just a speed limit imposed by the universe's cops. It's a boundary baked into the algebra itself. You literally cannot do math across that boundary.
It's like building a Lego set, where the blocks only click together if you obey the laws of physics.
That is a great analogy.
You can't build an impossible universe because the math just won't let you.
That's the idea. And the author doesn't stop at 2 dimensions. They scale this up. They introduce more units, L2, L3, L4, to build a multidimensional system. But they establish very strict rules. These units have to anti-commute.
Anti-commute. Okay, we hear that in quantum mechanics a lot. Remind us what that implies.
It means order matters. In normal math, 2 times 3 is 6, and 3 times 2 is also 6. They commute.
Right.
In this system, if you multiply unit A times unit B, it's the negative of unit B times unit A.
So A times B equals minus B times A.
Exactly. The notation is L mu times L nu equals minus L nu times L mu. This property is absolutely essential for the geometry to hold together without collapsing on itself. It ensures that everything stays orthogonal at right angles to everything else. It builds a rigid, grid-like structure for dimensions to exist.
Okay, so we have this hyperbolic anti-commuting mathematical engine running. We have a set of blocks that naturally describe space-time intervals. Now, how do we get from abstract algebra to a 5-dimensional universe? Because I'm looking at the title of segment 2 here, Space-Time Ultra.
Space-Time Ultra. I love that name.
I know, right?
It sounds like a superhero team or a high-end graphics card. Upgrade your reality to Space-Time Ultra.
It really does. Now with 20% more dimensions. So what's the setup?
The setup is this. The author defines a basis of 4 space-like vectors, dash all 4, L1, L2, L3. These all have a negative squared length.
Okay.
But then, to get the time-like sector, they multiply everything by that first vector, L4.
So wait, usually we talk about 3 spatial dimensions and 1 time dimension, 3 plus 1 reality.
Yeah.
Here we have, what are we looking at?
We have a 5-dimensional underlying structure. But the author argues that our reality, the 4D world we walk around in, is a specific projection or a slice of that 5D pie. The 5th dimension acts as an anchor.
An anchor.
It allows the transformation to happen, and this is where the author introduces what you call the magic function. They define a transformation called lambda of x.
Lambda. Okay, in cosmology, lambda is usually the cosmological constant dark energy. Is this the same thing?
Not quite, though they are related in spirit, as we'll see. Here, lambda of x is a function that defines what movement implies in this geometry. The formula is lambda of x equals x times gamma minus gamma v L4.
I recognize those terms. Gamma and V. That's Einstein 101. That's special relativity.
It is Lorentz-like, yes. E is velocity, and gamma is the Lorentz factor.
Right.
In standard physics, gamma is the thing that tells you how much time dilates as you move fast. If you get in a spaceship and go 99% the speed of light, gamma is the number that says 1 year for you is 7 years for Earth.
Right. But usually we apply those terms to a spaceship moving through space.
Exactly. And this is the critical conceptual leap. This author is applying these terms to the geometry of space itself.
Okay, let's pause and really unpack this. Applying velocity to the geometry. What does that even mean? Does the universe have a speed?
In this model, yes. The transformation splits the position vector into a tensor with upper and lower indices automatically. The draft shows that this operation generates one vector, x mu, with an upper index, and another covariant vector, x mu, with a lower index.
Hold on. Upper and lower indices. I know we have some physics students listening who are nodding along, but for the rest of us, why does it matter if the little number is up or down?
Great question. It's the language of general relativity. Think of it this way. Vectors with upper indices are like arrows pointing somewhere like displacement or velocity.
Okay.
Vectors with lower indices are like rulers used to measure those arrows like gradients or forces. To turn an arrow into a measurement, you need a bridge. That bridge is called the metric tensor.
The metric tensor. That's the map of gravity, right? The thing that tells space how to curve.
It's the rulebook for distance. It tells you how curved space is. Usually in physics class, you are given the metric. You start by saying, assume a Schwarzschild metric, and then you calculate. You bring the metric in by hand based on what you think the mass distribution is. But here
the author says, if we simply apply this transformation lambda, this movement function, the metric just appears. It generates a metric tensor, g mu nu, which is diagonal. It's -1 over v.
And that metric depends entirely on v.
Yes. And this is the selling point that I think is the most exciting. The metric isn't static. It depends on this parameter, v of t. The author calls it the ultra speed.
The ultra speed. So v isn't just a car driving down the highway.
No.
V is a property of the universe that changes over time.
Correct. The ultra speed v of t is a parameter that evolves from 0 to 1. Think of it as the universe's internal clock or throttle. When v is near 0, the universe behaves one way. As e approaches 1, it stretches.
And that's stretching. That's the expansion of the universe.
Precisely. The draft derives a scaling factor. The scaling factor is basically the number that tells you how far apart galaxies are. If the scaling factor doubles, the distance between galaxies doubles.
Okay.
The formula derived here is a squared of t equals v of t over 1 minus v squared of t. Let's look at that fraction. If v is 0, the top is 0, so the size is 0.
Right. The Big Bang singularity, a starting point.
And if EVA gets closer to 1, say 0.9, then the bottom is 1 minus 0.81, which is roughly 0.19. So the whole number gets big.
Exactly. As that speed gets closer and closer to 1, the denominator gets smaller and smaller, and the scaling factor shoots up towards infinity. The universe expands.
So just by having this internal speed dial turn from 0 to 1, you get a universe that starts small and gets huge.
Yes. And it gets really, really interesting when we look at how this matches up with reality.
Right.
This leads us into the third segment, cosmology and recreating the Big Bang.
Right, because anyone can make up a math formula that makes things get bigger. I could say the size of the universe equals the number of tacos I've eaten.
Right.
That number goes up over time, but that doesn't mean it's physics.
Mm.
The author claims this actually looks like our universe.
That's the key. In draft 1, there is a graph. The author plots this scaling factor against the standard lambda CDM model.
Lambda CDM, that's the standard model of cosmology. That's the one that requires dark energy and dark matter to work.
Correct. It's the model that fits the data from the Planck satellite and the supernovae studies. It's the gold standard.
But
remember, lambda CDM works because we inserted dark energy to make it work. We saw the universe accelerating, so we added a constant to the equation to make the math match the observation.
we patched the code.
We patched the code. But this author, they compare their ultraspeed curve to the lambda CDM curve,
What's the work?
and they match. Qualitatively, the curves look almost identical.
That is wild. So they didn't put in dark energy.
No explicitly named dark energy. The author assumes that this ultraspeed, v of t, grows as a slow exponential.
Okay.
The formula is v of t equals 1 minus e to the power of minus lambda t. So it starts at 0 and slowly creeps up towards 1, effectively forever.
And just that simple assumption, a speed dial slowly turning up, recreates the expansion history of the universe, including the accelerated part.
It seems to.
That sounds almost too simple to be true.
It feels that way, doesn't it? But sometimes the most elegant solutions are simple. By reverse engineering the expansion using just this growing speed parameter, the author suggests that what we interpret as dark energy pushing the universe apart might just be the geometric consequence of this ultraspeed approaching 1.
So we've been looking for a mysterious force, some fluid filling the universe, but maybe it's just the perspective shift of the geometry itself as it speeds up.
Exactly. And in draft 3, the author doubles down on this. They calculate the energy momentum tensor.
Which is the heavy lifting in relativity. That's the stuff in the universe, matter and energy.
Right. Einstein's famous field equations are basically gravity on the left side equals energy and matter on the right side. You tell me how space bends, I'll tell you how much matter is there. The author derives the density, rho, and pressure piece of the universe purely from this v of t and its derivatives, how fast v is changing and how fast that change is accelerating.
So matter and energy are just derivatives of geometry. They're not fundamental things you put in the universe, they're things the universe does.
In this model, yes. The equations they derive are, well, one of them is rho minus 3p equals 3v double dot minus 2 lambda. This connects the bending of space directly to the density and pressure.
This is sounding a bit like geometry is destiny.
It really is. And they check their work. They prove the continuity equation holds.
Which means energy is conserved, right?
Hey.
You can't just create stuff from nothing.
Yes. The equation is a bit messy to say out loud, but it basically means you aren't just creating matter out of magic. As the universe expands, the density drops in a predictable way. The math stays consistent with the laws of physics we know.
Okay.
But here's the part that I found fascinating. The end of time.
Ooh, ominous. What happens when rho finally hits 1?
Well, strictly speaking, it approaches 1 at infinity. It's an asymptote. But as time goes to infinity, the rate of change, the derivatives v dot and v double dot, they drop to 0. The speed stabilizes.
And what happens to the universe? Does it rip apart? Collapse?
It stabilizes.
Huh.
The graph shows that the density and pressure settle into constant values. Rho at infinity equals minus 3k plus lambda, and p at infinity equals minus k plus lambda.
So it's a stable, eternal, end state, no big crunch, no big rip, just equilibrium.
A Ricci flat vacuum, effectively. Which brings us to the biggest plot twist in these papers. We have talked about the fifth dimension as a mathematical tool, a scaffolding, but in draft 2, the author suggests it might be real and it might be curled up.
This is segment 4, the twist. And honestly, this is where my brain started to melt a little bit.
Yeah.
We're talking about a curled up dimension, like in string theory.
Similar concept, yes. In Kaluza-Klein theory from the 1920s, physicists tried to unify gravity and electromagnetism by adding a small, circle-shaped fifth dimension. This author is doing something similar, but for a different reason.
And that reason is?
They want the metric to be Ricci flat.
Explain Ricci flat.
Yeah.
Called it a holy grail earlier. Why do we want the universe to be flat?
In general relativity, the Ricci tensor represents the volume change of a ball of matter falling in a gravitational field. If it's zero Ricci flat, it usually means you are in a vacuum. Empty space.
But the universe isn't empty space. It has stars and planets and, well, us.
Exactly. So usually a Ricci flat universe is a boring, empty universe. That's the problem. We know there is matter. So how do you reconcile a geometric need for flatness with the existence of stuff?
You cheat.
You add a dimension. The author introduces a metric loosening transformation called gamma b. They introduce this fifth dimension, w, and say it is compactified on a circle with radius r.
So at every point in our 4D space, here in the studio, in your car, inside an atom, there's a tiny little circle of 5D space.
Exactly. But it's not just sitting there. There's an interaction between our time, t, and this extra dimension, w. The draft calls it frame dragging.
Frame dragging. That sounds like something from a sci-fi movie. Engage the frame drag.
It's actually a very real term from general relativity. Usually it refers to a spinning black hole dragging space-time along with it.
Like a spoon twisting in honey.
Yeah, the honey near the spoon twists too. Here, the author uses a term b of t to connect time and the extra dimension. It implies that the flow of time effectively drags this extra dimension along.
So time itself is the spoon.
In a way, yes. And this twisting creates a boundary. The math produces a killing ansatz.
Killing ansatz. That is the best name for a math term ever. Sounds like a thriller novel.
It's named after Wilhelm Killing, a German mathematician. It refers to a vector field that represents symmetry.
Okay.
When you apply this symmetry to the author's 5D setup, the math spits out a constraint. L squared is less than 4 eta over epsilon v.
Okay, let's translate that. R is radius. V is the ultra speed, since V is growing.
As E gets bigger, the denominator increases, so the value on the right gets smaller. Or, depending on the constants, the relationship changes. The key takeaway is that the valid region of the universe is tied to the speed.
A valid region.
It implies the universe has a geometric boundary that evolves as the ultra speed increases. We are living inside an expanding bubble of valid geometry.
That is slightly terrifying, but also really cool. It's like the universe is rendering itself in real time. But the real mind blower for me was the connection to quantum mechanics. I saw the Schrödinger equation in there. How on earth do you get from expanding geometric bubble to quantum physics?
This is the ecstatic selling point I promised. In draft 2, the author applies the box operator, also known as the D'Alembertian, to a field in this 5-dimensional structure.
The D'Alembertian, that's basically the wave equation in relativity, right? It tells you how waves propagate through spacetime.
Correct. It's the traffic controller of waves. Now, when you apply this operator to a standard 4D universe, you get standard waves. But when you apply it to this specific 5D setup with the curled up dimension W, the math simplifies in a startling way. An equation pops out that looks exactly like the Schrödinger equation.
The fundamental equation of quantum mechanics. The thing that describes probability clouds and electron orbitals.
The very same. The draft defines an effective potential V of size I equals n over 2r and an effective mass that depends on the velocity v.
So wait, are they saying that what we think of as quantum mechanics, particles, waves, uncertainty is just a side effect of living in this specific 5D geometry?
That is exactly the implication. The author is hinting that quantum mechanics isn't a separate set of laws. It's just what happens when you vibrate the geometry of the 5th dimension.
So the mass of a particle
is determined by the ultra speed of the universe.
That connects everything. Gravity, the Big Bang, and quantum mechanics, all tied together by this one parameter V.
It is an incredibly ambitious unification. If this holds up, it means mass isn't intrinsic to an object. Mass is a result of how that object interacts with the velocity of the universe's geometry.
And remember, this came from someone using textbook math and YouTube lectures.
That brings us back to the outsider narrative. I really want to focus on this for a minute.
Yeah, let's...
Because usually when we see grand theory of everything papers from independent researchers, they are, well, let's be honest, they're often unintelligible word salads. You know the type. Time is a cube, written in all cap.
I've seen those. They usually involve a lot of exclamation points and very little algebra. Einstein was wrong. Written in red crayon.
Exactly. But this is different. This is rigorous.
It feels different. The author apologizes for missing references, sure, but the derivation, they show their work.
They do. They start from a clear mathematical definition that L1 squared equals 1, and they follow the logic relentlessly. They don't jump to conclusions. They derive them step by step. The notation is a little unique, a little weird sometimes, precisely because they aren't copying the standard academic style. They're inventing their own dialect of math to describe what they see.
They're building their own tools because they can't afford to buy the standard ones.
Exactly. And there is a strength in that. It's unburdened by dogma. An academic might stop and say, well, you can't assume a scalar field like that because of paper X from 1984. This author just says, does the math work? Yes. Then let's keep going.
It's the joy of pure derivation. You can feel the excitement in the text. There are moments where the author seems to surprise themselves. Look what happens when I do this.
And that is a beautiful thing. Whether this model turns out to be physically true or not almost doesn't matter for our appreciation of it.
Yeah.
It's a monumental feat of construction. It's like someone built a cathedral in their backyard out of spare parts, and it actually stands up.
So let's recap this beast, because
Yeah.
we have covered a lot of ground, and I want to make sure I have the mental map correct.
Ideally, we can summarize it in 5 steps.
Okay, let's hear it.
1. The foundation. You start with split quaternion logic. You break the standard complex plane and make a hyperbolic one where L1 squared equals 1. This naturally creates the geometry of space-time.
The minus sign.
The minus sign. 2. The structure. You build a 5-dimensional space-time ultra using this logic. 3. The engine. You apply a Lorentz-like transformation, lambda, that turns the geometry into a moving, evolving thing. 4. The fuel. You let the ultraspeed parameter, v of t, grow from 0 to 1 over time. This drives the expansion.
And 5.
And 5,
Yeah.
the result. You get a metric that generates gravity, a Big Bang-style expansion that matches observations, and even a wave equation that mimics quantum mechanics via a curled-up dimension.
When you put it like that, it sounds strangely logical. Like, if you were a god designing a universe, this seems like a pretty efficient way to do it. Just set the dial to start and let her run to one.
It suggests that the complexity of our reality, galaxies, stars, atoms, you and me, might all be emergent properties of a much simpler underlying shape.
Yeah.
The author suggests the universe is conformally equivalent to the standard model.
Conformally equivalent. Give me the bumper sticker version of that.
It means the shapes match, the angles are preserved. It suggests that our complex reality might be a shadow or a projection of this simpler 5-dimensional truth.
That is the thought to keep you up at night.
It raises an important question. If reality is just a geometric shape expanding as a single parameter ticks from 0 to 1, what happens if we could control that parameter?
Oh, don't give them any ideas. We don't need anyone messing with the ultra speed of the universe. I feel like that's how you accidentally delete a galaxy.
Probably not. But it does make you wonder. If mass and gravity are dependent on v, then the fundamental constants of nature aren't constant at all. They are evolving history. Mass today might be different than mass a billion years ago.
We are just riding the wave of V.
We are.
Well, I don't know about you, listener, but I'm going to be looking at the night sky a little differently tonight.
Yeah.
I'm going to be thinking about that 5th dimension curled up everywhere, dragging time along with it, and that silent ultraspeed speedometer ticking up towards 1.
And remember, this theory didn't come from a billion-dollar particle accelerator. It came from someone just like you, curious, persistent, and willing to follow the math wherever it leads.
Absolutely. So, to all the learners out there, don't be afraid to open a draft, check the math, and appreciate the sheer creativity of it all. You never know where you might find the next Big Bang Theory. It might be in a PDF with no bibliography.
Indeed.
That's it for this deep dive. Thanks for listening. Keep diving deep.
See you next time.